computer. Okay. All right, the recording is started. Well, howdy. Let me go back to screen sharing here, but before I do anything else beyond that, let's ask the question, does anybody have any questions or issues or anything that has come up or anything you'd like to talk about? Cool, you're all good. All right. Wow, this is going fast. We are already in module 6, and there are only 8 modules, and then I've got an additional, these are hidden here, but I've got an additional finals week after that. Although for those people who really were counting on only 8 weeks and not going into a 9th week finals, what I'm going to do is when we get to module 8 to that week, I'm going to go ahead and open up the final during the 8th week so that you'll have both 8 and then the finals week after that to take that final so that you can take it anytime. So if you are hoping to get out early, then you'll have that opportunity to do that during the 8th week. Let's take a look at not lab 6, at week 6, the week 6 stuff. We're going to take on 2 topics here, and I kind of hate to take both of these on at the same time, but because we're crammed into 8 weeks, we're just we don't have many options. So we're going to talk about STP, or Spanning Tree Protocol, and VLANs this week. I've mentioned VLANs and you've looked at them a little bit. And oh, by the way, while we're here talking about this, let me mention that the labs last week, there were a lot of problems with the second lab last week, 5-2, I believe it is. Very few, I think only 2 or 3 people got 100% on the PKA file. And there are a couple of reasons for that. Here's the deal with those PKA files. Packet Tracer is, it's grading it itself by looking to see whether you've done something. And a lot of people said, well, for example, well, I put a description on the interface on the switch, and it didn't grade it. It still says that there's no description. Well, what's going on there is Packet Tracer gets messed up, or the grading portion of Packet Tracer gets messed up if you do things that it's not expecting. So in most of those cases, there's some command somewhere that you did that it was not asking for, and it messes up the grader. One of the things I found in the past that does that is the display name on a device. So if I have a switch and it says switch, and it says, well, change the host name to S1. So I change the host name to S1, and then I decide, well, I also want it to say S1 on the screen while I'm doing this. So I changed the display name to S1 as well, but it didn't ask me to change the display name. Well, now it's going to misgrade some of the things in the lab, even though they're not related to that. I'm not sure why it does that. I think because some of the things it's keying off of for example, in that case, the display name, in order to say, well, is this switch by this display name, does it have a description on this port? So it messes it up, and you have to be very, very careful. Another thing I'm going to tell you, and maybe I shouldn't, but I'm going to, if you look up if you get stuck and you look up on YouTube the name of the lab, quite often you'll find people who have solved them for you and walked you through them. The reason I'm not afraid to tell you that is that most of these people are going step by step by step, and they're explaining everything in great detail as to what they're doing and why they're doing it. And really, I find that I learn as much watching those when I'm stuck as I would if I looked it up on my own. So I encourage you to try to find things on your own. But if you don't, if you get stuck and you can't figure out, well, why can't I get 100% on this thing? I can only get 92% and I really want 100. Well, sometimes if you go back and do the lab again following those videos where somebody did get 100%, you'll see exactly what you did. You'll say, oh, wait a minute, I did this extra command that it's not asking me to do, and it's causing this grading to misgrade. So also, you'll notice that in the second lab, the router configuration, I didn't tell you how to do a lot of the things before you did them. For example, SSH. I haven't talked about how to set up SSH. The idea of SSH on a router or a switch is if a person logs in to either a port or the auxiliary port, let's say on a switch, I log into port F01 and I want to configure that switch using that port. Well, normally I would use Telnet. Well, Telnet, the only problem with Telnet is that it's not encrypted. And so I might want an encrypted connection in a workplace. And so what I would do would be to set up SSH, which is an encrypted version of Telnet. It's a later version of Telnet that was designed to replace Telnet. And in order to do that, there are several commands. Well, I didn't tell you anything about how to do those commands. And I left you on your own to figure it out and to do the research. You have the textbook. That information, for the most part, is in the textbook, or you can go online. But I find that when I look them up, when I get stuck in a lab like this, and I've taken many of these courses with many similar labs. In fact, I've done all of these labs in a course as well. And when I got stuck, I would go out and research on my own and not rely on Cisco's curriculum or notes or something. I would have to go out and then I would find that I would remember it a whole lot better. So that's why I do that, and I do it on purpose. My notes are skimpy in this course on purpose. So I think on the spanning tree protocol this week, if I remember right, yeah, it's a guest video lecture. And so you'll open up this Word document. Let's see, I think you're looking at my screen right now. Is that correct? Can you see my screen? Is it sharing? Yes, okay. So I put the textbook reading, of course, and depending on the version of the book you have, it may vary a little bit as usual. But this was based on the one that looks like this, the second edition. I don't know if you can see it or not because I can't see my own face on the screen, but the complete study guide. So that's what this one was based on. And if you have a different version of the book or a slightly, Lamley has written lots and lots of different books and they sound similar. One of them, for example, is almost the same name. It's the complete deluxe study guide. It's the same size as the other one, but things differ where they are. So if you happen to have that one or another one, you might have to change that. But anyway, I have this guest lecture on the spanning tree protocol notes. Let me go to these notes here for a minute. So right here, this guest lecture. And then I've given you just sort of a quick summary of some of the things in spanning tree. So let me explain spanning tree just a little bit, but not in great detail, because the lecturer here on YouTube does such an excellent job that I don't feel the need to reproduce everything. But let me give you the quick rundown. The idea is this. Let's say I've got a bunch of switches here and I've got them all interconnected. Now the first question is, why would I interconnect all these switches? And the answer to that is very simply redundancy. If a port or a line goes down, then I have an alternate way to get anywhere on this 5 switch network that you're looking at right here, 6-switch network, I guess. So I could put in a lot of redundancy. Now I could make this full mesh and have every switch attached to every other switch, but that would be a little overly redundant. And so the idea is to have this redundancy. But redundancy in this case creates a problem, and that problem is what we call a broadcast storm. Remember that switches are all on the same broadcast domain, which means that a broadcast, any computer that sends out a broadcast within that, on that switch, it's going to go to every other device, every other PC on any of the switches that are attached. So they are all on one broadcast domain. Well, let's say that a PC hanging off of here, let me see, I'll choose, I don't know if you can see my cursor very well over here, but I'm going to choose, say, this switch that sticks out in this little point here all the way to the right. I hope it's not reversed to the left on yours, but I think it's probably the same on the right. And so I've got a PC plugged into the switch on the right, and this switch has no idea who that PC is yet. It hasn't learned it yet. And as you probably know by now, and I'll remind you if you don't, the way that the switch learns who that PC is as soon as the PC sends something to that switch, like it responds to a broadcast, for example, or responds to another inquiry, then the whatever port that packet, or I should say frame, because we're dealing with layer 2, whatever port that frame comes in on, it has a source MAC address. In other words, the MAC address of that PC. And so the switch memorizes, okay, port 7 is associated with this PC over here. Let's call the PC AA, right? That's the MAC address. So port 7 is associated with the MAC address AA. That's not a complete MAC address, but that's okay. And so it now knows where that MAC address is. But let's say that this PC wants to talk to a PC over here on the upper left corner. Well, since these switches are new and they haven't yet learned where those PCs are, as soon as this switch A gets this, it doesn't know where to send this. It's going to send a broadcast, not a broadcast, it's a flood really. It's different from a broadcast, but it's going to flood that a query out of every port except the port on which it came in. So now you can imagine here you've got a frame going up here from switch A up to switch B, and another one going from switch B or switch A to switch F, which is down below there. And then those two switches are going to send something out on every port except the port on which it came in. So switch B is going to send something down to switch F. Switch F will send something up to switch B. Switch B will send something over to switch C. Switch C will send one over to switch D. Switch D will send it over to switch F. Switch F will send it up to switch B again. You can see what's going on. I've got a loop going on. And there's nothing to stop this loop. Now with routers, there is. With routers, we have something called a time to live. Every time a packet moves from one router to another router, it decrements that time to live by 1. So let's say that the time to live is 64. Well, it can only make 64 hops then, because it makes one hop to another router, it turns to 63, and then makes another one, turns to 62, and so on. And eventually it's going to die. It's going to get down to TTL, or time to live 0, and it's just going to drop the packet at that point. But with these frames, there's nothing like that to stop them from happening. And so STP is the way that we get around that. What we do is we block off certain ports, and you can see these red X's on this diagram. So these red X's are blocked ports that are intelligently blocked in such a way that there are no loops left. So now if on switch A, that packet is sent to, well, it can't send it directly to switch B. It's got to go down here to switch F and then up from switch F to switch B. Well, now it's not going to go anywhere from switch B because it doesn't send a frame out on the same port on which it came in. So it stops it dead cold. So everybody gets the information here, but nobody gets duplicate information, and it doesn't just continue on and on forever. Now, there are other ways to deal with this. There, for example, layer 3 switches, which act as both a router and a switch, so to speak. It's not a full router, but you can use entirely layer 3 switches. Or you can move your data to layer 3 data such that it's not running or not moving around by MAC address, but that's not normal on a local network like this. Local networks typically use MAC addresses as their addressing system. So that's what's going on. STP is simply blocking these ports. So the question is, well, how does STP know? And the way that it does it is it just chooses one of the switches as sort of the master switch. We call it the root bridge. That harkens back to the days when a switch was a simpler device. Switches used to have only 2 ports on them. And they did the same thing switches do today, but they only had 2 ports, and we called them a bridge. So we call it a root bridge. Sometimes you'll see root switch, but not very often. So it chooses a root bridge, and that root bridge then becomes the master way that everybody tries to communicate. So in other words, everybody looks to see what is the shortest path to that root bridge. And what it's going to do is look at the different path costs based on the types of lines. So for example, a telephone modem would be a very low path cost, and then a fiber optic would be a very high path cost. And I have these put in here. So a 4 megabit per second link would be a cost of $250, 10 megabit per second cost of $100, and so on. Actually, I set them backwards. The low cost is good. So the fastest is here at 10 gigabit per second with a cost of 2. So it's looking for the lowest cost. And so each one is going to choose, well, one of these ports is the lowest cost to get to this root bridge down here, this one that's circled in green. And then we're going to label each of these things. You'll see the little RP, that's the root port. That's the port that is designated as the lowest cost in order to get to the root port. And so the RP, or the root port, is always going to be left open. And then we're going to designate some what we call designated ports. Those are the ones that are not necessarily blocked, but they're not the root port either. They're not the fastest way to get to the root bridge. And then once we get designated ports, once in a while we're going to get a case where I've got several designated ports, and I need to choose how to block one. And so we're going to use the same system that we do for choosing the root port, and I'm going to go through that in a minute, in order to decide, well, which one should be blocked. And the rules, let me see, here are the rules up here somewhere. Okay. By the way, I said those frames that I said the switch is going to send out these frames. The frames are called BPDUs. I just call them BPDUs. I don't know what else to call them. And that's the name of the type of frame that switches send out when they're exchanging information in order to to find out which ones are going to be the root ports, which ones are going to be the designated ports, and so on. So the root bridge is chosen first. The switch with the lowest bridge ID made up of the bridge priority and MAC address is the first choice. So the bridge ID is a bridge priority, which is always the same on all switches by default. Now you can change the bridge priority, and then the MAC address. And so the two are concatenated. You got the bridge priority, which is 32768 by default. And then you just concatenate onto the end of that the MAC address. So you got 32768 and then a number, whatever the MAC address is. Now, if all of these switches have the same bridge priority by default, then that means what's really determining the root bridge is going to be whatever the lowest MAC address is. Now, if you think about this, it's a problem, or it could be a problem, because how are MAC addresses designed or created? Well, the MAC address is created by two parts. It's a, let me get a notepad up here. Can you all see the notepad? Did that pop up? Yes. Oh man, I got this down. I figured this out. So first of all, I have, in order to make a MAC address, I've got 6 pairs of hexadecimal digits. And the first pair, or I mean the first 3 pairs, I'll say AA. These first 3 pairs are the vendor, the ID of the vendor. They call the OUI. And so I don't remember what it stands for, don't ask. Each vendor is given a set of hexadecimal digits. So Intel, these are yours. Netgear, these are yours, right? So let's say the AA belongs to Netgear. And then Netgear in turn is going to start cranking out MAC addresses on all of their network interface cards. So they're going to start typically like this: 00, 0000, right? And the next one's going to be AA 000001, right? So basically a serial number. So the second half is the individual number that company has put out in order of manufacture. So if I'm looking for the lowest MAC address, well, guess what happens? It turns out to likely be the oldest switch that I've got because it's the lowest MAC address. Now, it could be that, let's say, another company, BB, has a 000001 like that. No, let's make that 00. So this is a different company. In this case, this 1 is lower than this 0 because this one starts with AA and this one starts with VB. So this is a different company. I believe in the video that I put up for you to watch this week, he makes a statement that it's always the lowest, always the oldest switch. Not necessarily. It could be that it's from a different company and that different company has a lower OUI, and so that's actually going to be a lower MAC address, even though it's a newer switch, for example. So he made a mistake in that, in saying that. But you can see that the tendency is for it to be the oldest switch. Now, the oldest switch is also likely to be the slowest switch. So it's not likely that I would want the slowest switch to be my root bridge. Why would everybody try to send data in such a way that it maximizes the use of that particular switch, of the oldest switch? That is one of the reasons I might want to change the bridge priority. I can't change the MAC address. Well, I can, but typically you don't. The MAC address is a physical burned-in address, and you could fool it, but why do that, right? So the bridge priority is going to be the determining factor most likely. Well, the MAC address is the determining factor by default, but if I want to make a different bridge, my fastest switch, the root bridge, I might want to lower my bridge priority on that particular switch. And then if everything else, let's say that all else is equal and it doesn't know what to do, well, it's going to choose the port number with the lowest cumulative cost to the root bridge. And then the path that has the least hops is the next tiebreaker. And then the port connected to the neighbor switch, which has the lowest switch ID value. And then finally, the port which receives the lowest port spanning tree port protocol value from the neighbor switch. That's a mouthful. We never get down into this range. You don't really need to worry about these very much. If you know this much of it, the MAC address, and then the port number or lowest cumulative cost, and remember that the port number is the, is that in here? Port number, oh yeah, the port number of the next bridge, next switch is the next tiebreaker. So if you remember that much. So let's take a look at this one and see if we can figure out what's going on here. I got to get closer because I've got stronger glasses on. So in this case, I've got, let's see, switch A over here, 32768 is the priority. On B, 32768, C is 32768, 32768, 32768. This one down here, yeah, these are all the same priority value. So all of these have the same potential to be the root bridge. So the next tiebreaker then is the lowest MAC address, and you can see this one, A here is 0000000000000A. And then let's see, yeah, down here, the one that's circled in green is 0000000000003. Well, 3 comes before A in the hexadecimal numbering system. You go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So 3 is lower than A. So, and then the others are what? D, C, and B. So you can see that it got that far. Now, you're not going to have 2 MAC addresses the same, but let's say that for some reason I did. Let's say that for some reason I actually went in logically, manually, and messed with these MAC addresses so that they both have the same MAC address. Well, what's it going to choose then? Well, it's going to choose the lowest path, the lowest overall cost to get to any one switch. So it's going to take all of the, let's see, it's going to take this switch and figure out the cost of this switch, this switch, this switch, this switch, this switch, right? And it's going to try to decide which one is going to be the fastest way to get to it from most of the other switches. So it's kind of gets kind of complex. Now, when I'm choosing ports, root ports, there's another factor, and that is, well, what's the port number? If I have 2 equal cost paths to a switch from another, let's say I've got equal cost this direction from D to F to E as I have from D to E, right? And so the costs are the same. Well, it's going to choose the lowest port on the receiving switch. So in this case, let's see, we got a G01 and an F01 down here, and I'm not sure which way it goes on that. Probably the G01. So it would choose that route rather than the other route. So it would choose that particular connection or that particular port as the root port. So that's yet another tiebreaker. The rules are the same for choosing root ports as for choosing the root bridge, except you also have that port number that comes into play. Now, I know that's all kind of confusing, right? There's a lot of stuff. And you have, by the way, you have the capability of changing these costs. You have the capability of changing the bridge priority. that's pretty much it as far as the capability. As far as capabilities you have in altering this thing. We're not going to really get into altering these very much at the level that we're at in this class, changing priorities and changing, well, you certainly change port numbers, but changing priorities and changing the cost values. So we're not going to get into that particularly in this course. But if you go on to the CCNA level, then you'll need to be able to do that. I encouraged you here, if you listen to this guy, which is a little bit shorter one, and you struggle with it, you might want to listen to this longer video here. And if you still struggle, then I would encourage you to go out on YouTube and just find some other videos. And just keep listening to them until one of them sinks in. Let's see, that's pretty much it for STP. It's a little confusing, but after you listen to this guy's longer version, rather than my 10-minute thing here, and you're still confused, then let me know, or continue to listen to some other videos. Do I have questions about STP? I mean, don't worry about it if you don't, something is a little bit unclear, but if like a whole concept is unclear, that'd be a good thing for me to clear up right now. The details, don't worry about the details until you listen to these other videos. It's not. Okay. VLANs. VLANs is next. Let me back up here to notes and resources. VLAN notes. VLANs are pretty cool. So I've given you a picture here of how VLANs work. The idea of a VLAN is that you're going to separate a switch into various subnets. And these are actual subnets. So you go, well, wait a minute, switches only deal with layer 2. Layer 2 only deals with MAC addresses. So how can switches have subnets when subnets are a layer 3 address, an IP address? Well, it turns out that switches today are relatively smart enough to know about how to address IP addresses, enough to make VLANs anyway. You don't need a layer 3 switch for this, by the way. A layer 2 switch does this. And I'm going to describe a little bit about how it's doing it, what it's actually up to. So this switch that you see right here in the middle on the screen is, in this case, it's a single switch, right? We don't have two switches going yet. And I'm going to talk about a 2-switch operation or 3-switch operation in a minute. So what I'm going to do is I'm going to say, I'm going to tell the switch programmatically, I'm going to tell the switch that I want 3 of these ports here. Let's say that the VLAN 1, these 3 PCs that go to VLAN 1, the engineering VLAN, are ports 1, 3, and 5. So I'm going to tell it ports 1, 3, and 5 are on VLAN 1. All right. And I'm going to tell it ports 2, 4, 6, and 8 are on VLAN 3. And then ports 9, 10, 11, 12, 13, and 14 are on VLAN 2. So now what happens is, let's say that this laptop down here in the bottom left corner wants to send a message to the farthest laptop away, the one on the other side there. So it sends a message up to this switch. And as a matter of fact, let's not even make this an independent, let's make let me back up. Let's make this a broadcast just for fun. So switch A here, the PCA here, or the first laptop, sends a broadcast message out. And it sends that out up here to this port, I said was 2, the first line down there on the bottom left. And when the switch receives it, it tags that frame. and it tags it as a 3. This is a VLAN 3 frame. Now it's going to send that broadcast out of everything that is a VLAN 3, and it's going to strip the tag off before it sends it. So it's not, the PCs are totally unaware of what VLAN they're on. They have no clue what VLAN they're on. But the switch keeps track of the VLANs, and it adds the tag when it receives the frame, and then it strips the tag back off when it sends the frame back out. However, the trick is that these laptops must all be on the same IP network. And if they're not on the same IP network, they're unable to communicate with each other, unless it's a layer 3 switch. Now, layer 3 switches have a way of getting around it, but we're not going to deal with layer 3 switches in this course. So that means that what if I want this laptop, this first laptop, to talk to this first PC up here in engineering, the first laptop in accounting to talk to the first PC in engineering? Well, the truth is, the way it's set up right here in this particular image, it can't be done. I need a router. I either need a layer 3 switch, which has some routing capability, or I need a router. And that's what we're going to deal with next week, is something we call inter-VLAN routing. How do I get from one VLAN to another VLAN? How do I set up a router in a way to do that? And there are two ways. There's a traditional routing method, in which I would have a router hanging off of here with 2 ports, two lines to the switch, and it would go out one line, which is on VLAN 1, and come back on another line, which is on VLAN 3. Or I would set up something called a router on a stick, which is kind of a funny name, but a router on a stick only has one line between the switch and the router, and it's capable of running 2 different VLANs. So let's see, I don't have a, oh yes, I do have an image down here with 2 switches. So let's take a 2-switch scenario. Let's say that here I've got, as you can see, I've got VLAN 100 on host A, VLAN 100 on host B, VLAN 100 on host D, VLAN 100 on host E, and then I've got VLAN 200 on host C and host F. Now, how am I going to get information from, say, host A to host D? Well, when I send the frame for host D up to switch A is going to put that tag, that VLAN 100 tag on that frame. And it's going to send, let's say it doesn't know where D is, so it's going to send a frame out of every port except the port on which it came in. And so it sends one down to B, it sends one to C, and it sends one across this trunk line. Well, the idea of the trunk line is that it can carry any tag. Whereas these guys down here, these ports are only responsive to one particular VLAN. So in other words, B and D and E here are going to be the only ones that'll ever hear a VLAN 100. But this port here, the trunk port up here, can carry 100, 200, any other VLANs I have across it. So the trunk port is a very specific type of port, and you have to set it up on the switch and say, this is a trunk port. If it's not a trunk port, it's an access port. The access ports go to the individual computers, trunk ports go to another switch. So it's going to tag that as VLAN 100, carry it across the trunk line, and then switch B over here is going to say, oh, VLAN 100, let's see, that's D and E, and it's going to send that frame out to D and to E, but not to F, and it's going to strip the tag off. So that's how we deal with multiple switches. By the way, let me back up here because I didn't mention this with STP. One of the things that STP is really good at is when you have something called ether channel. Ether channel is when I have more than one line going from switch to switch. So I pick 2 ports out, and well, 4 ports, 2 on each switch, And I make a line going across from, two different lines going across from one switch to the other. And ether channel is very good for either failover or load balancing. And when I do STP, I would block both. If a particular port is blocked, it blocks the entire ether channel, both sides of the same line. So line A and line B here, they both be trunk lines. If they're not blocked, if they're if the ether channel port, it's kind of a combined port, right? It looks to the switch like one port, but it's really two. If it's not blocked, if it's a root port, then of course it would act as a trunk and carry it across, just like you're seeing here. So that's essentially how VLAN works. Now, the thing is here with STP and VLAN, STP is set up automatic by default. In other words, if I just plug a bunch of switches together, STP will spin up and start running and work flawlessly, unless I want to make changes. I might want to make changes to the bridge ID or some other change, but other than that, it just works. There are other flavors of STP. There's PV-STP, RSTP, various flavors of STP that Cisco uses. It turns out that we usually just say STP, but the flavor that Cisco uses is actually RSTP plus. Don't worry about that, but just for your information. But now with VLANs, VLANs are not automatic. In a sense, they are. Every port on a switch, as the switch comes out of the box from the factory, every port is automatically on VLAN 1. So there is a VLAN 1, and everything I connect to that switch is already on VLAN 1. But VLAN 1 is also set up as something we call the native VLAN. The native VLAN is one that does not tag. And I can have one native VLAN on my ports or on my switches. It's not good security to leave the native VLAN as VLAN 1. It's best security to change it to some other VLAN. Most typically, what you do is you set it to a VLAN that you're not going to use. I would put all of the ports that I'm not using on switch A here, for example. Any port that's not plugged, doesn't have something plugged into it, I would put it on its own separate VLAN, and I would make that the native VLAN. The reason is that if somebody tries to hijack my switch by pretending to be another switch and pretending to be a trunk port, then as soon as I plug another switch in, it's going to try to negotiate. By default, it's going to try to negotiate a trunk line when I hook from switch to switch. So if a bad guy plugs a switch or a PC that has software on it to emulate a switch, they can send untagged information to that switch normally and hijack the trunk port. And so what we want to do is make all of these ports a kind of a trash can VLAN, a VLAN to nowhere, and then make that our native VLAN. So the untagged traffic would go to Never Never Land and never go anywhere to any other devices. We also can have a management port. In order to have a management port, what I would need to do would be to set, believe it or not, an IP address on some port. And that's the port I would plug into if I want to communicate by Telnet or SSH to that particular switch. And I can do all my management through that. And no other devices should be on that VLAN, so that only the administrator can manage that switch and somebody else can't come along and switch over to that VLAN and manage the switch. So there are various types of VLANs. There's native VLANs, management VLANs. and then just VLAN VLANs. Let me go to, I'm going to open Packet Tracer. Any questions at this point, by the way? Let me see if I can open the chat so that I can see the chat window. Okay. All right. Packet Tracer. I presume you're seeing Packet Tracer. Is that true? Seeing Packet Tracer? Yes, good. All right, let's get a switch here. Whoops, wrong device. 2960 is always a good switch. In fact, I don't know that I need two of them, but I'll put two of them there. By the way, here's what I was talking about earlier. Oh, it's still booting. I have to wait for it to finish booting before I can do anything. Looks like it's ready now. The display name. It says switch 0 on here, and if I change this display name, sometimes it messes up the grader on Packet Tracer Labs. Anyway, so let's go into this switch, and I'm going to go into the command line, enable, and I'm going to do a show run. Well, let's see if we can find any information about VLANs in here. And here's all my ports. Well, here we go. Interface VLAN 1. Well, what's that about? I don't have an interface called a VLAN. However, I can. If I put an address on VLAN 1, in other words, I say interface VLAN 1 in my configuration, and I put an IP address on, this now VLAN 1 becomes my management VLAN. So that's the idea. By the way, we call this an SVI, this address. Well, I'll be doggone if I can remember what that stands for, but the SVI address is the management address that we would use for VLAN 1. And VLAN 1 is shut down right now by default, by the way. So there is no VLAN, but I don't see any information about any other VLANs here. Well, that's an interesting point. If I want to see what I've got set up on here, I can't do it in the running config because it doesn't exist in the running config. It exists here in, let's see, this is flash memory. Flash memory holds my, actually holds my operating system itself. Right? That's in flash. But so let's see, I'm trying to remember the command. Let's do a show VLAN brief. If I look at VLAN brief, I can see that there's a bunch of VLAN information here. So in other words, here's VLAN 1, and it's got all of the ports that are on VLAN 1, and it's all the ports. And then I've got some other VLANs here. I've got a VLAN 1002, 1003, 1004, and a 1005. These are built-in VLANs that are always there. We don't use them for anything else. These are reserved for such things as token rings and fiber rings. So they're kind of pretty much legacy, but they're left here for for legacy purposes in case you have something that needs it. Let's see. I'm trying to remember. Let me look here and see if I can remember where you see the. Here it is, the flash. Show flash. No, not flash. Bear with me for a minute while I try to remember where it is. But there's a file called the VLAN.dat file, which is where all of the VLAN information actually exists. I cannot remember. Let me Google this for a second and see if I can remember where to find that. So that's not the command I was looking for. That is not the command I was looking for. Well, I can't remember it off the top of my head. I'd have to look it up again, and I'm having a hard time finding the command that I was looking for, but such is life. But anyway, you can see the vlan.dat file. I just can't remember how to get there. So one thing that I want to do, though, while I'm here is I'm going to go ahead and go into configuration, conf T, and I'm going to go interface F05. I'll take that one. And I'm going to change this. They're all access ports by default. In other words, they're ready to connect to a device. So, however, they can change to trunk ports instantly. They're set up by default. If I plug another switch in, it will automatically detect that and change to a trunk port. Well, that's a bad thing. It's a good thing in that it makes switches work easily, but it's a bad security thing, because if somebody else comes along and plugs something into that port, let's say a PC with software on it that emulates a switch, they can make that PC a trunk port. Now the trunk port's going to see all the VLAN from every tag, so it's going to be able to see all the VLAN traffic from every VLAN on my switch. I don't want that. Right? That's a bad thing. But let's turn this port F05 into a trunk port. And the command we would use to do that is switch port mode trunk. Now, I have designated this port as a trunk port specifically. So now if that bad guy PC plugs into F05, it will not negotiate into anything else. It will, of course, it is a trunk port now. Let's say I do instead a switch port mode access. Right? Now, only a PC can talk, and only on whatever VLAN that port is on, and it cannot become a trunk port. Now, there also is a negotiate mode, which is the one that it is by default. I'm going to go back to trunk port, and I'm going to turn that into a trunk port. And then I'm going to back up. I'm going to back up twice. And I'm going to do a show VLAN brief. Oh dear, it's going to make a liar out of me. Switch port mode trunk. Oh, it's because I don't have another switch connected to it. That's why. All right, let's connect these two. Oh, this thing's going so slow. It's not. There we go. Let's connect these here. Switches like that. And which one did I connect? I didn't even choose the port. Let's try this again. This time I'm going to connect them with a crossover cable from port 5 to port 5. There we go. Yeah. All right. So let's make switch port mode trunk on the other switch as well. And so I'm going to go enable conf t interface F05 switch port mode trunk. The line is now changed to up. So these two are communicating now. Let me go move it ahead. These two are now communicating as a trunk port. All right, now hopefully this will work for me. Show VLAN brief. There we go. That's what I was looking for. You may notice in this list that port F05 is missing. And this really throws people off at first. You go, well, let me just check my VLANs and see if ever, what ports are on what VLANs. And so you do this and you go, wait a minute, what VLAN is F05 on? And you can, you drive yourself nuts trying to figure this out. Well, it turns out that it's a trunk port, and it wouldn't make sense to say what VLAN it's on because it's carrying all of the VLANs. By the way, I can limit it with configuration. I can say I only want this trunk to carry certain VLANs, but it doesn't show it here. And so instead, I'm going to go back here to show and down. Show, and again, I never can remember the show commands that I want when I want them. So I have to take a look at this help system to do it. I believe it's under interface. Let's try that out. Oops. Yeah, show interface trunk. That's it. Oh my goodness, how long is this? Show interface trunk. And now I can see, oh yeah, here's port 05, and it's a trunk port. This other it also shows me, by the way, that it's on VLAN 1, and VLAN 1 is the native VLAN. It tells me that it's trunking. It's in trunking status right now. It also tells me what we call the encapsulation type. Encapsulation type is 802.1q. What this is the protocol that this switch is using, or that's being used on that port in order to tag it. And there are a couple of different protocols that could be used. The other one is called ISL. ISL, and I can't remember the name or what the acronym stands for, but ISL is Cisco's proprietary protocol. But it turns out that it didn't work very well, and it was never very popular. And so Cisco has gone back to the open source protocol, the 802.1q protocol, for tagging everything. Now, why is that important? It's important when we get to inter-VLAN routing. When we start setting up router on a stick, I have to create a trunk port between a switch and a router. And the switch knows that the encapsulation type is 802.1q, but the router doesn't know that. And so on the router, I will have to program that it's an 802.1q trunking encapsulation protocol. So that will be important later on. But as you can see now, I know all of the ports and all of the ports and all of the VLANs that those ports are on that are trunking rather than access ports. Otherwise, I can do that show VLAN brief. And by the way, show VLAN and show VLAN brief are very, very similar. The only difference is you also get this little table down here at the bottom when you do a show VLAN, when you do the non-brief version. and it just gives some additional information. So that's VLANs. We're going to do, when we get to the lab this week, did I close this? No, there it is. When we get to the lab this week, we're going to do 2 different labs here for VLANs. So let me go down to labs and assignments. Spanning tree protocol, this one is not self-grading. There is a spanning tree protocol lab that is self-grading, and I chose not to use it because it is, there's not much to it. Remember I said STP is all automatically running, right? As soon as I plug a switch in, STP just works. So there's not much to configure. So I found this lab. This is a earlier Cisco lab that has a little bit more to it than the lab that I found that has the automatic grading to it, which actually was so simple it didn't even have anything to grade. It said, here, look at this. That was all there was to it. In the VLAN one though, open that up, you'll see I've got 4 files here. 2 of the files are the PDF files, and I hate the way this thing sets this out. You can't tell which ones are PDF and which ones aren't. Okay, that's the PKA. So I've got 2 PKA files and 2 PDF files, and of course, like last week, the PDF, these 2 are the PDF files. The PDF file is simply the instructions. So this one, the first one here, 3.3.12, I think is the first one, is just simply VLAN configuration. And then the second one, 3.4.5, is configuring the trunks. So things like determining what VLANs can run across what trunks, for example. Which one's the native VLAN and that sort of thing. Says one thing Cisco does not do very well in this course or in their course is they have a security course in which they do a pretty good job of telling you how to set up security, you know, to change the native VLAN from VLAN 1 to some other VLAN, and to set up all of the non-used ports as a sort of a trash can, you know, VLAN to nowhere. They don't tell you all of that stuff in their earlier courses, and it's kind of a shame that they don't. But you'll have 2 of these to do, and each one will be worth half the grade. So if you get 100% on both of them, then that's worth the full 10 points. Get 100% on one of them, it's 5 points. Yeah, and then you know, prorated between that. So if you had 100% on one of them and 50% on the other, that would be 6.67 points out of 10. Or no, yeah, that'd be right. No, it wouldn't be. It'd be 75. That's 7.5 out of 10. You see Dogecoin? Yes, I Dogecoin. Yes, I do. I do mess around with Dogecoin, and some of the other. I'm not a big miner, although I mine a little bit here and there, but just for fun. Any other questions about VLANs or about these labs this week? Let me get the chat back again. Okay, let's go back down. Let's see, I don't think I have any surprises here in the quiz, just quiz on STP and VLANs. On a lot of these quizzes, by the way, maybe I think I've done it on all of them. I put a really long time limit. The reason I do that is because, you know, I have students at all different levels of capabilities. So for example, you know, I get a lot of requests from the disability services that says, hey, give this person time and a half or double time on a test. You know, maybe somebody has vision problems and they have to, you know, it takes a lot longer to read the questions and that kind of thing. And so what I do is I just put this big 12-hour, or not 12 hours, is that whatever, 720, yeah, 12-hour time limit. And that way it's not considered the actual time limit. It's just a long time. And I actually have to put an actual limit, because if I don't, what happens is a lot of people open the quiz, walk away and leave it open, and it never closes. And I don't have the capability of closing it at my end. And so every time I go into the grades, it looks like something needs graded, and it's just abandoned quiz attempt. And so this forces it to close after 12 hours if somebody doesn't, you know, somebody walks away from it. So that's what that's about. Okay, that's pretty much it. STP and VLANs. As usual, when you listen to the lectures and when you do the labs, you'll learn most of the stuff. I'm not doing a lot of detail in my little lectures here. Trying to think if there's anything else I really need to cover today, and I can't think of anything. You open this window up so I can see all of you. I don't know, you probably don't see the actual window, right? Does it, when I'm looking at the Zoom, big black Zoom window with everybody's pictures, you don't see that, is that correct? Okay, good. So chat, where's the chat window? There we go. Okay, no questions, no problems, no.
When you were doing that example in Packet Tracer, what was it? Do you, if you have one switch port, like if you switch one port to trunk, does that make it so that somebody else can't connect the switch to a different one and it sets an automatic trunk between them, or do you have to set all of them to like access and trunk?
Well, I have to set both of the switches, the ports on both switches to trunk, obviously. Well, I don't have to, because by default they negotiate and they'll look for whatever this is on the other side. But as soon as it sees a trunk, it'll set itself up as a trunk. However, yeah, once I set it up as a trunk, it is a trunk, no questions asked, and it stays a trunk. Is that where you were going with that, or did I miss it?
I guess so. We were just talking about that example where if somebody wanted like to
somebody plugs in. Yeah, somebody plugs in port.
So the other ports, they don't care that this one was established at a trunk. They'll, if the other ports are still like or the modes weren't switched to just strictly access, they could still automatically turn into a trunk.
They will become a trunk by default. Yeah. So that's bad. First thing typically that you'll do is, well, not the first thing, but one of the first things you'll do if you're doing good security is to blanket make everything access, and then make the ones trunks that you want to be trunks. That way you are turning off that auto negotiate feature. That helps block anybody from that kind of a hack.
Cool. Thank you.
Yeah, that's called trunk hijacking. It's also possible. There's a couple. Well, I'm not gonna. There are other types of trunk hijacking as well, but yeah, two or three names, and they're very subtle differences between them. And if you ever take the CCNA course, you kind of have to, go through those subtle differences. But good question. Any other questions? No. Wow. This camera here like makes me really close, and I can see I need to shave. All right. If no other questions, then I think that I don't have anything else to cover for today unless there's something somebody would like me to talk about or would like more detail about. But apparently not.
I did actually have a quick question.
Sure.
I feel like during one of the labs last week, in Packet Tracer, when you pull up that like the actual diagram of the switch itself, is there a button on? Is there a power button on that diagram somewhere, or?
Well, the power is on by default. Let me go to let me get rid of this thing here, minimize it. There we go. So no, the first of all, the switch is always powered on as long as it's plugged in, and there's no power button on a switch. There is on a router, and if I pull up a router, there we go. If I pull up a router, you see in physical mode here. Let me zoom that in. In physical mode, I have a switch. If I go to the physical mode on a switch, you'll see I don't have a switch, a power switch. So yeah, they're all on by default. Is that getting to what you were trying to ask?
No, yeah, that's exactly. I figured I saw something online about like the router, I mean, turning the switch on and off, the physical switch, but I was just wondering because I couldn't really zoom in on that thing, so.
So what happens on a router quite frequently in packet tracer exercises is it will be expecting a WIC, a serial port, and you don't have a serial port maybe on that router. So you have to turn it off, pull that port over, and it's always a WIC. WIC 2T is the one you're always looking for in that case, and then turn it back on again, and it'll boot back up. But yeah, with a switch, as long as it's plugged in, it's always on. So let me see if I can get back to the participant list here. Any other questions? I hope that answered it sufficiently.
Yeah, thank you.
Right, man, I got to get used to this. Got to get used to how this Zoom thing works. Sometimes it's very confusing to find how to switch back and forth between views. But at least I figured out this screen thing, so I don't have to keep switching that back and forth. What I need to do actually is get a second screen here and have my Zoom stuff on one screen and my screen on the other. So maybe one of these days I'll do that. All right, well, I guess we'll cut it off here then. And I got to remember to get into the recording and stop the recording. I'm going to stop the recording. Stop video. There we go. And we'll cut it off. So thanks for being here. I guess that's all.
Thank you, sir. See you next week.
Thank you, Professor. Have a good night.
Take care.
Thank you.